Hello, my name is Tom Helmuth, and today I'm going to be telling you about a new suite of program synthesis benchmark problems that was developed by me and my student, Peter Kelly. These benchmark problems are in the area of general program synthesis, also sometimes called software synthesis or automatic programming. These types of problems aim to resemble those types of problems that are solved by humans when they program. This means that they involve multiple general purpose data types, such as strings, integers, booleans, floats, etc., as well as control flow structures, such as conditional execution, loops, and recursion. Program synthesis here falls under the umbrella of supervised learning in that the specifications for a given problem are provided as input and output examples. So given this input, we want a program that produces this output. Now, general program synthesis has been tackled by genetic programming as well as other non-GP systems of doing synthesis. And we are aiming our benchmark suite to be available to both GP and non-GP methods. So I want to give you a little history about program synthesis benchmark problems. Starting before 2015, there was really a limited set of problems that people used for benchmarking. And these problems tended to have a few things that I'd consider undesirable. For one, these benchmark problems typically had very limited instruction sets, small set of often domain-specific instructions. And these problems were often what I would consider toy problems, simple problems that would not be of the type we would expect to see in the real world. Now, this was the case both in genetic programming and in other inductive program synthesis fields. One example of a problem here is the Santa Fe artificial ant problem, where this sort of meets all of these certain descriptions. And so because of this sort of lack of good benchmark problems, there was a push in the early 2010s in genetic programming to introduce better benchmark problems. And partially because of this push, in 2015, I, along with Lee Spector, introduced the first general program synthesis benchmark suite. From here forward, I will call this PSB1. And PSB1 contained 29 benchmark problems that were taken from introductory programming homework problem sets. In other words, these were the types of problems that we expected humans to solve when they were learning to program. Now, this PSB1 benchmark suite has been used to benchmark at least 10 that I know of GP and non-GP program synthesis systems. And this brings us to the present, where here we're going to be talking about PSB2, a new set of benchmark problems. And so you might be wondering, why do we need new benchmark problems? So I'm going to talk about some reasons that we have a need for new benchmark problems at this point. One important piece of this puzzle is that in the 6 years since the PSB1 was introduced, a variety of synthesis systems have been applied to it and have improved their results on this suite of problems. In fact, many of these problems ended up to the point where we can solve them most of the time. And at that point, there's not really much room for improvement, which would be useful when you're trying to show that, say, a new method gives you improvements. And so we have this need for new, harder problems in order to drive research forward. Now, I want to think about how difficult a problem is in two different areas. One is subjectively, and here when we, as you'll hear, when looking for new problems, we tried to pick problems that we expected to be more difficult than those in PSB1. And then objectively, when we ran our GP system on the new problems, we didn't want to include any that were solved, say, more than about 2/3 of the time. And in fact, almost all of the problems had success rates of less than 10%. Finally, we want to make sure that the field doesn't start to overfit on one set of problems. This is an issue that has been seen in machine learning, where particular benchmarks were used repeatedly until methods started to barely be able to make any progress, as well as the systems really started overfitting those benchmark problems, and the improvements seen on them didn't necessarily reflect improvements that would be seen on the real world problems. And so a big reason that we need these new problems is simply to keep moving the field forward and make sure we don't stagnate on one set of problems. Now, there's some issues with PSB1 that we kept in mind when creating this new benchmark suite. So for example, in PSB1, some problems tended to run much more slowly than others, which caused issues when doing experiments with the suite. Also, some problems ended up being too easy. We, for genetic programming, could solve them almost every run in a small number of generations, while other problems were simply too hard. They were never able to be solved by any synthesis system so far. Another issue that we wanted to avoid here is that PSB1 ended up being difficult to implement new systems. Now, we still saw it adopted in at least 10 different systems. Still, we had major goals for making PSB2 easier for new people to implement and test in new systems. Finally, we wanted to make sure there's a lot of consistency with hyperparameters. In other words, we wanted to make sure that across problems, we kept a consistent set of hyperparameters, such as number of training cases, the population size, the number of generations used in genetic programming, and so on and so forth. This is going to make experimentation and comparisons easier, where in PSB1, we actually recommended a variety of hyperparameters, and that led to difficulties in experimentation. Now, I'm going to start talking about the problem sources that we used in order to choose problems for PSB2. The main majority of the problems in the suite came from websites dedicated to providing problems for users to practice their programming. So these go beyond those sort of designed for introductory students to learn how to program, and go to look at more advanced programmers, or at least more moderately advanced programmers, and their abilities. First up, we have Code Wars. Code Wars is a site where users can create coding katas, which are used for practicing programming skills. Similarly, Advent of Code is a website that every December releases 25 new programming challenges that are some fun and some sort of challenging, in order to give users a chance to also practice their programming skills. Project Euler is a bit different of a motivation. All of the problems on Project Euler are more mathematical in origin, but all of them are programming problems. And so Project Euler aims to have problems that programmers can use to think about programming in math. Finally, a few of the problems come from homework sets. And so these were actually from the classes that I teach at Hamilton College to undergraduate students. Note that these aren't all, in fact, most of these aren't from introductory classes. Most are from, say, 200 level or upper level classes in our curriculum. And so this gives you an idea of where all of these problems are coming from. Now, let's get to the problems themselves. For the second benchmark suite, we decided to choose 25 problems after considering over 75 problems and implementing over 50 of them. Now, after all of these implementations, we looked to get a set of problems that had a few characteristics. One, we didn't want these problems to be too hard or too easy. So we looked for problems that fell in that middle sweet spot. We also looked for problems that had a variety of requirements, whether that is different data types, different control flow structures that they might need to use, and so on and so forth. Now, over to the right here, I have a table of the input and output types across all problems in PSB2. And so you can see that for at least inputs and outputs, we require different problems to use integers, floats, strings, booleans, and then vectors of integers and floats. Some of these problems might use other data types, such as characters, but those never were the input or output types. I want to look at two of these problems in particular to give you an idea of what a few of these problems look like. So first up, spin words. In spin words, the program is given a string as an input and must take that string, find all of the words in that string, as the words are separated by spaces, and then every word that is 5 or more characters long must be reversed, and then all of the words glued back together. So we have this example here. If our input is hello all at gecko, we then want to reverse hello and gecko since they are 5 characters long and keep the other words as they were, and glue those back together as a string. Now, that problem is a bit more, is very focused on strings. I wanted to give you another example of a problem more focused on numbers. So here in the vector distance problem, we simply give each program 2 n-dimensional vectors of floating point numbers. And the program must find the Euclidean distance between those 2 vectors in that n-dimensional space. I'll note that for this problem, we give the program vectors with dimensions between 1 and 20. And so that means that the program has to figure out how to iterate over the vectors in order to find these Euclidean distances. So for example, here we have 2 3-dimensional vectors, and finding their Euclidean distance gives this out. So now that we've looked at the problems in PSB2, we also want to talk about how we expect people to use PSB2, because we don't want this to be something that just we use. We want this to be something that can be widely adopted and used for benchmarking in genetic programming and in the program synthesis field more generally. Unlike PSB1, we made some changes that are designed to emphasize ease of use. And one of the big things here is that we're providing data sets for every single problem that can be sampled to produce the training and test data for each run. So this means that each, say, genetic programming run can use a different sampled set of training data as well as unseen test data in order to make sure we get sort of different examples used in different runs. Additionally, we are going to provide Python and Clojure libraries, possibly others in the future, that allow users to sample this data without having to write those samplers themselves. This link here with a QR code takes you to the Zenodo page where you can find the data sets and these sampling libraries. Finally, I want to talk a bit about some experiments that we conducted to get a baseline of these problems. Now, even though PSB2 can work with any program synthesis system, here we used PushGP, which was used quite a bit on PSB1, in order to get some initial results. Now in PushGP, programs are nested lists of instructions and literals that can be sort of any level of nesting. And Push uses a stack-based interpreter in order to interpret programs. For these experiments, we used a large general purpose instruction set. Now, because different synthesis systems will need to use different instruction sets, we don't specify a particular instruction set, but we recommend that sort of very general purpose instruction sets that have a large number of instructions be used when using PSB2. As for error functions, we used very standardized error functions per data type. And so, for example, with integers and floats, we, when the output is an integer or float, we find the absolute difference between the program's output and the correct output and use that as the error for the GP system. Similarly, when we have, say, a string output, we find the Levenshtein string distance between the output string and the correct string and use that as the error value. For our GP runs, we are recommending using a fixed budget of 60 million program executions per run. We've divvied this up into 300 generations over a population size of 1,000 with 200 training cases. That's sort of what we're using, but other systems might make different choices here with the same budget of program executions. Finally, our performance metric here is success rate, and we expect programs to be, we expect systems to be measured on how many runs produce successful programs out of, say, 100 runs. So I'm going to quickly look at some initial results here using Push. On these 25 problems, 13 of the problems were solved by our Push system, As comparison, with PSB1 at this point, 26 out of 29 problems have been solved. And so we can see that many problems still need to be solved in PSB2. And additionally, most of these problems haven't been solved more than, say, 10 times if they've been solved at all. As another point of data as to the difficulty of these problems, here are the program sizes of solution programs after they've been simplified. You can see that the sizes here vary from about 9 to the mid-30s. And as a comparison, in PSB1, 8 of the 29 problems could be solved with fewer than 9 instructions. So we can see that more instructions are needed to solve these problems, showing again that they are more complex. So quick conclusions here. We've created a new suite of program synthesis benchmark problems that are easier to use than those in PSB1. And we've shown some results showing that these problems are more difficult than those in PSB1. We hope that this new suite of benchmark problems can continue driving the field of program synthesis forward in the years to come. Thank you.